In my last lecture, I described and used an elegant theorem for finding rotational inertia that's called the parallel axis theorem. There is a related theorem that is referred to as the perpendicular axis theorem, and to illustrate, let me use the hoop here once again. We already know from a previous lecture how to set up an integral to find the rotational inertia of the hoop. As I rotate about an axis like so, the axis is passing through the center of mass of the hoop and is perpendicular to the plane of the hoop. Imagine, however, taking the hoop and rotating it about an axis that is perpendicular to that. That is, about an axis like so, or say an axis like so. Setting up and evaluating the integral to calculate the rotational inertia in such situations is rather difficult to do. However, there is an elegant theorem called perpendicular axis theorem that allows us to make the calculation actually fairly easily. There is, however, a restriction placed upon perpendicular axis theorem, and that restriction is that it only applies to what are essentially two-dimensional objects, what are referred to as planar lamina. So in other words, the distribution of matter is two-dimensional, whereas we ignore the third dimension of negligible thickness. So it applies, for example, to a hoop, it applies to a disk, but it doesn't, for example, apply to, say, a sphere. So I'll illustrate the restriction upon perpendicular axis theorem after I derive it and use it in a simple situation. So I'm going to draw basically a two-dimensional object. Okay, so here's what is referred to as perpendicular axis theorem. Okay, I'm going to go ahead and draw out three-dimensional coordinates, x, y, and z. And then let's say that the two-dimensional object is in the xy plane. So in other words, its third dimension in the z direction is of negligible thickness compared to its dimensions in the xy plane. So right here we'll say is basically this two-dimensional object like so. Okay, now right here is a small piece of it, a little m sub I, and then here's its distance from the z-axis. So I'm using summation symbols. I'm just going to go ahead and write down what the rotational inertia is about the z-axis. Right here is a little r sub I. So I sub z, as it's called, so this is taking the thing and rotating it about the z-axis like so. That's equal to the following summation, m r squared. However, now I'm going to think of the distance r in terms of an x and y coordinate. So for example, right here is an x sub I associated with a little m sub I. Right here is a little y sub I associated with a little m sub I. Let me now go ahead and write r sub I in terms of x sub I and y sub I, and let's see what happens when I do. Like so. Okay, now let's write each term individually. Like so. Okay, take a look at each term. Notice that each term is an mr squared, if you will, all by itself. Each term is a rotational inertia. So this right here is describing the rotation of this red object here about which axis? Well, it's referring to this distance x sub I away from the y-axis. So it's as if you took the red object and you rotated it about the y-axis like so. It's the rotational inertia about that axis. This guy right here is referred to as I sub y. Okay, and then right here is another rotational inertia. It's an mr squared type of calculation. But take a look at the y sub I. The y sub I is describing this distance right here. For m sub I, it's the distance away from the x-axis. So it's as if you took the red object and you rotated it about the x-axis like so. This is referred to as I sub x. Like so, and that's it. That's the rotational inertia then of each individual axis added together to get the third. This is perpendicular axis theorem. So it's a very simple derivation. Let's just take a look at one example. And then after we look at that example, we'll look at the restriction as well. Okay, so the example that we'll take a look at is the hoop situation that I've been using here to demonstrate. Use the perpendicular axis theorem to find I sub x and y sub I if I sub z for a hoop is equal to mr squared. So let me go ahead and draw this out. All right, so here's our hoop example. What I'm going to do is draw the hoop in the XY plane. So here's X, Y, and Z. Okay, so here's the hoop in the XY plane of mass M, radius capital R. And we already know what the rotational inertia is like so about the Z-axis. We've seen this previously as ICM. This is mr squared. So we already know what the rotational inertia is about the Z-axis. It's ICM, it's equal to mr squared. Okay, now here is perpendicular axis theorem. Okay, what does I sub y and I sub x look like? Well, watch this carefully. First of all, I sub y. I sub y is the rotational inertia about the y-axis, like so. That then looks like this. Okay, and then the second term is I sub x. The x-axis is like so, pointing straight out of the board, so then therefore we're asked to find the rotational inertia I sub x like this. So take a look at it again. Here's I sub y, and here's I sub x. We're asked to find h. What's the answer? It's 1/2 mr squared. They're both the same. There's no physical difference between the two. It's a symmetrical situation. So once again, here's I sub y, like so. And then secondly, here's I sub x, like so. They're exactly the same. So because of symmetry, I sub y is equal to I sub x. So if they're the same, then mr squared has to be 1/2 mr squared plus 1/2 mr squared. That's the answer. As simple as that. So under the right conditions, applying perpendicular axis theorem in a problem such as this is actually very simple and straightforward to do. Okay, now here's a situation where perpendicular axis theorem does not apply. Here's a three-dimensional object like so. This is a sphere. Okay, you can ultimately set up and evaluate an integral to find ICM for a sphere. It involves a triple integral. It's not done at the AP level. So imagine rotating it like this about the z-axis. If you rotate the sphere like this, the rotational inertia of a sphere is 2/5 mr squared. Okay, now right here would be I sub z, 2/5 mr squared. So right here would be I sub y. Right here would be I sub x. Are they the same? Yes, they are by symmetry. However, do they obey perpendicular axis theorem? No, because this I sub z is 2/5 mr squared. This I sub x is also 2/5 mr squared, and this I sub y is also 2/5 mr squared. Because the sphere is rotationally symmetric, it doesn't matter which axis you're talking about, x, y, or z, you always get the same thing, 2/5 mr squared. So therefore, 2/5 mr squared plus 2/5 mr squared cannot be 2/5 mr squared. In other words, the sphere does not obey perpendicular axis theorem, and it's because it's a three-dimensional object. So that illustrates the restriction that is placed upon perpendicular axis theorem.